So in keeping with really a more general idea in this course that I would really stress you want to get good at, is we see a lot of, well, graphs for you to interpret. And when they throw a graph at you, one of the things, what I would like you to be able to do is, first of all, pay very careful attention to what the units are or the quantities are on the graph. So is it a velocity versus time graph, for example? And then when you look at a velocity versus time graph, and this is a terrific example of this, they got both of the, let's call them tricks, I don't know, but they have both phenomena I'm going to talk about in one problem. So if you have something like this for a velocity versus time graph, we could even go like that. There we go. So from point A to B to C, there are really two possibilities that will generally be the case. I'll say three possibilities. And one of them is a simple case where all you have to do is read a piece of information off of the graph. You know, they give you a certain time and you know a velocity, and then you have to figure something out about that. That's, to me, the most basic case. The two things that I really want you to focus on are this. If you have a graph, the two quantities that are going to be possibly important are slope and area under the curve. Now, I'll say under with quotation marks, because if you have a graph and part of that is below the x-axis, what we're really referring to is the part of the graph between, the area of the graph between the graph and the x-axis. So that would be the area, quote, under the curve. So would this, and so would this piece here. So sometimes those areas can be negative. They're always between the graph, however, and the x-axis. So those two possibilities. And what I want you to get good at is looking at this and identifying reasonably quickly which one you want to work with. Or even if you're not sure, here's what I would do. I would take a look at the two quantities, and remember that slope, and this is the part where you have to know this, the fact I want you to remember is slope, remember, in a very rough sense, is y over x. Right? I know it's change in y over change in x, but it's definitely y over x. That means this is velocity divided by time. If that, for example, here doesn't trigger anything, use the units. This is meters per second, of course, and this is seconds. So velocity over time would be meters per second, which when you simplify it is meters per second squared. And somewhere in here, hopefully something triggers. You're like, oh my gosh, that's acceleration. Either the change in velocity over time or the units might trigger something, and you might realize, oh my gosh, oh my goodness, there we go, I mixed three things. That's acceleration. I know I can find the acceleration. All I got to do is find the slope of this. Or I know right here there is no acceleration because the slope is 0. So the first general idea, remember we're thinking general, is take your graph and look at, see if the slope is going to help you. So put your y over your x and see if something shows up. It might not. And if it doesn't, let's look at area under the curve. Or even if it does. Sometimes, like in this graph, there's information in both. Area under the curve is always going to be the y times the x. So it's going to be velocity times time. Now, use the units again. Well, it's meters per second times seconds. That's just meters. Ooh, that's distance, or in this case, displacement. So a velocity versus time graph has both. Slope means something, and the area under the curve means something. And you, depending on the problem, you might have to use, potentially either one. So let's look at here's an example from your homework of a force versus displacement graph. Now, when you look at this graph, let's do what we just did. So we have F, not too worried about the cosine right now, but F times force times distance, right? Or force and distance, I should say. If I look at the slope, that's force over distance. I can't recall a quantity that involves that. You might remember a Newton is that's newtons over meters per meter. That is a kilogram meter per second squared. That's a newton over a meter. That's a kilogram over a second squared. I don't recall ever discussing a unit like that. And yeah, so that slope doesn't seem to be telling me much of anything. But, I mean, it tells me that how the force changes as I move, but it's not a quantity we study. What about the area? Well, I want you to take force times distance. Right away, hopefully, having studied work and energy, you recognize right away, and by the way, this is really net force here. You recognize right away, oh, wait, that means the area under the curve is work, is the net work done in this case, because they give us the net force. So, by the way, really that's the crux of this entire video, is that when you have a force versus displacement graph, the area under that curve is the net work done, or the work done by that force. It depends on whether they're talking about net force or a single force that is not they're not looking at the combination of all the forces, just the work done by a single force. But, and if you look at it in terms of net force like this, the area under the curve is the net work done. Okay. Now, as far as this problem is concerned, and by the way, finding the area, we'll discuss that in a second. As far as this problem is concerned, you might be like, well, yeah, but they're asking about the speed of the object. I have two suggestions. Either rewatch the video on the work energy theorem, but even so, even if you're doing this in a couple weeks and we haven't done energy in a while and a problem like this pops up, this is an example. Just go with what you know. If you know that the area is work, the area under the curve is work, find it and see if something triggers to remind you about the work energy theorem while you're doing it. So let's find that area. That area I'm going to separate into a triangle. This blue triangle here, and a square. I guess it's a square. So the area of the triangle is 1/2 base times the height. The base is 10. The height is 10 newtons. So 1/2 base times height, that's going to be 50. So the area under here is a positive 50. What would be the unit? Newtons times meters or joules. This is going to be 10 from here to here times 10 this way. So that's going to be 100 joules. So we're looking at a total network of 150 joules by looking at the area under the curve. And then for this problem, like I said, I would point out that remind you that the net work done is always equal to the change in the object's kinetic energy. And I'm betting that if they want the speed at the end, yep, they give you the speed at the beginning, and it's at rest. So that really what you're looking for is that change in kinetic energy really just becomes the final kinetic energy, because that's going to be KE final minus KE initial, but this, since it started at rest, is 0. So really, 150 joules equals the final kinetic energy, 1/2 mv squared, and you go ahead and find the speed from there. Now, work, as we know, can be negative. So be careful about that. Here, the net work done would be positive. It would result in an increase in the kinetic energy of the object. But here, the net work is negative, which means that would be a decrease. This could be like friction or some other type of force pushing against it as it moves in the opposite direction of the force. So be careful about that. This is negative work, and this is positive work. And if we want the net work done from 0 to 4 meters, we would have to combine them as such. Find the area of the negative section, find an area of the positive section. And of course, if the force is 0, no work is done, which makes sense. So be careful. Work can be negative. As far as finding the area of this, I'll let you roll with it, but it's they give us the force. So, for example, here, that's going to be a 1 meter by, I think according to this, 7.9, negative 7.9. And you could figure out the area and so forth. And this is going to be really the same thing but cut in half because the area of the triangle. So bottom line is work is the area under the curve in a force versus displacement graph. Remember the versus. This is versus. Remember, it's always y versus x. If you're ever wondering, which one's the x, which one's the y, it's always y versus x is the way it works.